Oh, good afternoon. Today we're going to be looking at systems of equations and matrices. Let's see.
Well, you go through and
There's a different computer. The one in our normal classroom
you may
is.
as well click all of those and get your checks there.
There. How long did it? Oh, these are broken into two parts, aren't they? Yeah. Okay. How long is that? I don't guess it matters. And hold on.
Pearson ones have the transcripts, all the bells and whistles.
Okay.
But it's sort of strange that if you watch those Pearson videos, the way they just start. And today we're going to. But anyway, today we're going to be looking at something called systems of equations. If you recall in a previous algebra class, if the phrase elimination and substitution sound familiar, then you've already done this before. But if we think about drawing two lines, what we're actually going to be doing is finding points of intersection of lines. If you drew two slanted lines like that, intersecting one point,
one unique solution. That system of equations has one unique solution.
Well,
solving a system of equations means finding the point or points of intersection. And in most cases, when you're looking at two lines, there's one unique point of intersection.
Now, would it be possible to draw two lines intersecting in exactly 2 points? Say no. No way you can draw two lines that intersect in exactly 2 points.
Well, we could have two lines that never intersect. Yeah. What are they called? Two lines that never intersect.
What are those called? Starts with a P. Remember that from geometry?
Parallel lines. They have no point of intersection, so their system would have no solution.
And there's one other case, and that would be if you were drawing two lines, if you drew one line on top of the other. How about you drew one line on top of the other?
That's called coincidental lines. One line on top of another. How many points do they have in common then? All of them? So there are infinitely many points of intersection. Those are called coincidental lines, but for our purposes,
one on top of
just one line on top of another.
So we're going to look at a lot of different several different methods for finding these points of intersection. And why don't we just go ahead and start with problem number 1. We're going to
mention the two common methods, substitution and elimination. There are two generally accepted methods, and I think problem number 1 they're asking for is substitution.
I'm going to demonstrate substitution for you. Let me see. Oh, really? That's so small.
Hold on. It's not letting me. Okay, hold on.
Can you make it bigger?
I'm trying. Control. Shift. No. Plus. You're right. Plus. Is that bigger?
A little bit bigger. Yeah, I think that looks good.
That looks better.
Okay. So what we have here, we have two lines. Remember, with an equation, if there's x's and y's and no intersection, those are lines.
No exponents.
Excuse me, no exponents. So we have the line 4x plus 3y is negative 12.
And x equals
10 minus 4y.
We're trying to find where do those two lines intersect. If you drew the graphs, where do they intersect?
And you're saying that as if they're supposed to just answer you, but that's what you're trying to find.
And realize the instructions. Make a note. It said to use substitution.
Mm-hmm.
So write out substitution. Yeah.
So I'm demonstrating substitution.
Realize substitution is not my preferred method. I prefer the other method, elimination, but with substitution, you need to have one of the equations solved for a variable.
Like this one, the red one?
It's already solved for x.
Isolated. So
if your equation is, your system of equations are set up like that, where one of them is already solved for a variable, then, okay, substitution's a good method to use.
With substitution, what we're going to do is we started off with two equations and two variables. I'm about to write one equation with one variable. By the way, I should have mentioned that our answer is an ordered pair. So that means it's going to be an x and a y. So
write that right there. 1 point, parentheses, x comma y.
Okay. So with substitution, you take the equation that has the variable isolated and you substitute into the other equation. So right here, in place of this blue x, I'm going to put minus 4y. I'm substituting this equation into the other equation. And by doing that, I now just have a single equation with y. We know how to solve that for y. We know how to isolate y. Well, the first thing we'd have to do is distribute the 4. So we have a 40 minus 16y. Then I carry down the plus 3y equals negative 12. This is just a linear equation. Isolate the variable. We'll do that by combining the negative 16y plus 3y. That would be a negative 13y. And then what am I going to do with this 40 if I'm trying to solve for y? I'll have to move it over by subtracting. Negative 12 minus 40. Is that going to be a negative 52? Only one thing left to do to isolate y. What do I need to do to both sides? Divide both sides by that negative 13.
So we know these lines are going to intersect at a point whose y coordinate is positive 4. We know half of the ordered pair. If we were to draw those lines, which we're not going to, but they would intersect at an ordered pair whose y coordinate is 4. And just like the name implies, we're now going to substitute again to find the value of x. It's generally easiest to substitute into the equation where x is already solved for. You could say, oh, I'm going to put the y right here, the 4 right here in this blue y. That's just more work. You're trying to find x, so substitute the 4 into that red equation where x is already by itself.
So we have x equals 10 minus 4 times y. In place of the y, I'm putting the green 4. So what do we have? 10 minus 16. Is that going to be a negative 6? See how I got a negative 6 for my x value? So we don't have these two lines graphed. All we know is that they're what? Two slanted lines. How do I know they're slanted? Well, there's x's and y's.
Remember, if the equation has x's and y's, the lines are slanted.
And so the
two lines intersect at the point negative 6, 4. Any questions there? So when we go to my lab, here are the two. Notice
put
B
in the
and
answer,
C.
and then I'll tell them how you can tell.
Negative 6, 4. Okay. And check.
Okay, now, for those other two possibilities, if here are the special cases, which you're not going to, I don't think they ever pop up. Okay, Tim?
Oh, let me switch over.
If, when you're going through all this work, if everything subtracts out,
and you get 0 equals 0. The variables subtract out, you substitute, and everything subtracts out.
Yeah, right down here, instead of getting a y equals, you get 0 on the left and 0 on the right.
Infinitely many solutions.
That's the coincidental lines that you were talking about. Infinitely many solutions. Now, if, on the other hand, when you're going through all this work, everything subtracts out, and you have a 0 on one side and another number on the other side.
That's not 0. Well, when does 0 equal a number that isn't 0? Never. That means the lines never intersect. They're parallel.
No solution. So I want to mention that, although it doesn't actually happen, but you're going to see the solutions. And they might get, I suppose they might get a mistake. They might make a mistake and wind up with 0 equals 0. Oh, then you're going to choose the infinitely many solutions. You just messed up. Okay?
Let's look at number 2.
Okay.
Let's see.
There's another one that says use substitution.
Oh, it says to use substitution. Now, the beauty of this is once you see elimination, if you decide I like elimination better, we wouldn't know. If you solved using elimination on a test, when it said use substitution, you'll still get the same answer.
I'm more interested in getting the right answer
than the method that you're using. But if you're going to use substitution, okay, has everyone written it down that's writing it down? Okay, realize for substitution, you need one of the equations solved for a variable.
You need one of the variables isolated.
I don't think we have that here.
So which one of these variables would be the easiest to isolate?
I highly recommend you solve for the variable that won't give you a fraction. There's only one variable you can solve for that you don't have to divide by and get a fraction. Okay, so the variable that's just, has a assumed 1 as its coefficient. That's what I recommend you solve for. So solve that. Let me switch over to your paper. You're right.
Okay. So this is the smart. If you were going to get this x by itself, ultimately you have to divide by 3. Here you have to divide by 5. There you'd have to divide by -2. You don't want a fraction. If you have to get a fraction,
use another method.
Substitution. Use another method. So I'm going to get this y by itself by moving the 3x. So I would have y equals -3x plus 17. And now I'll start doing that substitution. Take this. Since it says y equals, I'll plug it in for this black y right here. Are y'all caught up? 5x minus 2 times -3x plus 17 equals 10. So I'm replacing this y with the -3x plus 17.
By the way, you cannot decide, oh, I'm just going to substitute that in back over here into the same equation. You solve one, you substitute into the other. You have to use both equations.
Now I'll distribute this -2, so I have 5x. Is that going to be a plus 6x? And minus 34 equals 10. linear equation, so get all the x's together and then isolate the x. Well, 5x plus 6x I can write as 11x. And what am I going to do with this minus 34? Yeah, add it over here to both sides still. Yeah. 10 plus 34, is that a 44? Are we going to get another 4 as an answer on here?
What I'm impressed by, or what I'm glad about, is that we're not getting a fraction. You could get a fraction. It's just Pearson is just being nice, giving you an integer. Because whatever you get, what are you going to have to do? Suppose you got whatever number you get here for x. You're not through with the problem. What are you going to have to do? Plug it back in up here. At least you're not having to plug in a fraction.
Mm-hmm.
So
we now know the x value is 4. So I'm going to plug a 4 in for x.
To get y.
Y is negative 3 times x. X is 4 plus 17. So what do we have in a negative 12 plus 17? What are we getting for y? Y equals, is it 5? So follow what we did there. Substitution is not my preferred method. I prefer elimination. And so,
well, let me type in the answer that you got. So parentheses 4 comma, was it 5? Oh, what did I do?
What did you do?
I don't know. Oh, parentheses 4 comma 5. What am I doing wrong?
Oh, the number lock isn't on.
Oh,
there.
of course. 4.
It's hard to work with technology when you get a certain age, isn't it, Tim?
Oh, shut up.
Okay.
My sister's still trying to master the touch screen on her touch screen phone. Oh, I don't want to be like her.
Oh.
She got her track phone, her little folding phone in 2001 or so, and she kept it as long as, and finally they just announced no.
They told her no, and
it was cut off, and so now she's forced into having to deal with the touch screen phone. Oh goodness.
Yeah.
I
Okay.
don't want to be like that.
Solved by the elimination method. Let me write this one down. The elimination method is the method I like, but in order to do the elimination method, you have to have the like terms lined up. Show them what we noticed.
Notice they have the x's lined up, the y terms lined up, and on the other side they have the constants lined up. So this is tailor-made for elimination. And with elimination, we're going to do exactly what the name says. We're going to eliminate one of the variables. What you want is, you have the variables lined up, the like terms are aligned. You want the same coefficient on both variables, but with opposite signs. I believe that the x's are the ones that we'll want to eliminate. If the coefficient on x is a positive 1 in the first one, what's the coefficient on the second x? Negative 1. You want the same variables, the same coefficients, but opposite signs.
You're gonna let me make a note. This is elimination.
Once you have the same the same coefficients, but opposite signs, you add them up. Let's add. X plus a negative x, 1 minus 1. What's about to happen to the x's? So they've been eliminated. That's the name of the thing, the method. Now let's add the y's. 5y plus 7y gives me
12y.
Add the constant terms. We're adding the two equations together. 46 plus 50 gives me 96.
Now, can I isolate y pretty easily? What do I need to do?
Divide by 12. Good.
What's 96 divided by 12?
Is it 8? Yes, it is. That means the lines are going to intersect at a point whose y-coordinate is 8. And y'all see why we say it's the y value? Because that's the variable we just solved for, the y. Now, if we were using strict elimination, we'd then say, okay, we need to start back at the original problem. Okay, 7 and 5 and 7. They're not the same numbers. Well, we can multiply up here by 7, multiply down here by a -5 to get a 35 and a -35. But we don't have to use strict elimination. Once you know one of the letters, what can you do to find the other one? Plug it into one of them. It doesn't matter which one. It doesn't matter which equation. May as well use the one that doesn't have any negatives.
I think I'd plug it into the first one. So x plus 5 times y equals 46. The 5 times y, 5 times 8, so what do we have? X plus 40 equals 46. And subtract 40, what are we getting? X equals 6. You know what? We haven't even mentioned that there's a way you can check your answer and see if it's right.
Plug it into one of the equations. Plug in 6 to both of them.
Plug in the 6 for X and the 8 for Y. And see, do you get a 46? Oh yeah, we'd have 6 plus 40. Okay. Check down here. -6 plus 7 times y, 7 times 8 is 56. So -6 plus 56, is that given a 50? Yeah. So I don't even need to, well, if this were a test, I know it's right. Okay? So plug it in.
Here, type it in. 6. And this number 3 is tailor-made for elimination. Suppose we don't have.
I think number 4 is tailor-made for elimination. Also,
in the previous one, we eliminated the x's. In the previous one, we eliminated the x's. Which letter are we going to eliminate in number 4? What would be the easiest letter to eliminate? Yeah. Why? Because we have the +6 and the -6. We have the same coefficient but opposite signs on the y's. So I would say eliminate the y's.
Okay.
So 8x plus 6y equals 16 is the first equation. 8x minus 6y equals a -32. That's the second equation.
So adding vertically, this one is tailor-made for elimination because the y's get eliminated.
Now 8x plus 8x, what's that going to give us? 16x equals
16 minus 32. Is that a -16?
Yes. And then what do we have to do to solve for x? One step remaining. Divide by 16 to give us x equals -1.
So the x coordinate is -1. I need to figure out the y coordinate.
Which one do you want to plug into? It doesn't matter. The top equation or the first one or the second one. Which one do you want to use? I always say use the one that has the fewest negatives. Okay?
So
and
8x,
well, you recopy an 8x plus 6y, so they know what you're using.
Too late. So, in the first equation, in place of x, I'm putting that -1. And the 8 times -1 is a -8. I'm feeling sort of wishy-washy right now.
I think you're misusing the word.
Yeah, I am. Oh, I can't believe it's the last lecture of the semester, of the year. Huh. Okay, I'm just talking. Do y'all finish it up? What am I going to do here? I will
add 8 to give us 6y equals 16 plus 8 is 24. And then divide by 6 to give us y equals 4.
Y equals 4. This is called elimination. And the natural question, I guess, to ask is, well, wait a minute. What if it isn't just tailor-made like that? Well, let's look at number 5. If we just add vertically on number 5, are we going to get one of those to, variables to cancel out? It looks like we get like a 9x and a what?
2y.
2y. So
you need the same coefficient but opposite sign. I think, hey, we have the opposite sign on the y. We have the opposite sign. We have a positive and a negative, so we're halfway there. At least we have opposite signs, but we need the same number. What's the trick to get the same number? Remember, you can multiply both sides of an equation by any number you want to, except for 0. You can't multiply by 0 because then you just make everything equal 0 equals 0. But we can multiply the second equation. We have a positive 3 there. We can multiply the second equation by 3. And then what are we going to have there in front of that y? I haven't written it down. I haven't switched over yet, so don't bother writing. But once we multiply the second equation by 3, what are we going to have here in front of this y? So we'll have that minus 3y that'll subtract out. But let's look at the thing on paper. So we're multiplying 3 by 3. So I would have a, let me rewrite the first equation. I'm not changing it. 6x plus 3y is negative 12. And what is this going to be, a 9x? Now here's where we're getting what we wanted. A minus 3y equals, is this going to be a negative 3 on the right? Yes.
Now if I draw the equal sign, the horizontal equal sign, if I add vertically, notice the most basic problem-solving strategy. I took problem 5 and made it like number 4, didn't I? I'm multiplying that second equation by 3. Now what would we have here? We would have a 15x, the 3y's gone, yeah, equals, is that a
negative 15?
Negative 15. Now divide both sides by, and we're getting x equals what? Negative 1.
So these lines are intersecting at an ordered pair whose x value is negative 1.
Well, we have x, so what are we going to do to find y? Here's my x. X is negative 1. That's going to be my answer. Ordered pair. But I need a y value. Well, which one do y'all want to plug into? First equation or the second?
You'll get the same answer either way at the end for y. First one?
Yeah,
okay.
I think that's the one I was going to use. So 6x.
So we're plugging into the first equation.
So in place of that purple X, I'm putting a -1. And 6 times -1, that would be a -6. Ooh, this looks messy. Can y'all read my purple writing? And let's see. How would I solve for y? Well, I'll just move that 6 over by adding 6. So we would have a 3y equals, if I add 6, am I going to have a -6 over there on the right? And then divide both sides by 3 to get y equals, oh wait, I'm out of room, -2. So -1, -2 is my point of intersection. We're going to see another method called Cramer's rule that I think works really well if your answers are going to wind up being messy fractions like -17 over 38. Because I don't want to be plugging that in. Okay, so
I'll do some matrix stuff.
Okay.
Okay.
This problem is a good one to go fast on.
Yeah.
Okay, so
here. First of all, what do I mean by a matrix? A matrix
in algebra
is just a rectangular arrangement of numbers. So rectangular arrangement of numbers.
So if you write some numbers in a rectangle, then that's what we call a matrix.
And the plural of matrix is matrices, matrices.
I think that was in the title of this assignment.
You're right. Generally, we enclose a matrix in rectangular brackets. It looks like those brackets used for interval notation. Okay, something like 3, 7, 0, 5, 1, -4.
He's just made up a matrix.
I've just made up a matrix. There's a matrix. Some terminology. The horizontal alignments are called rows. This is row 1, and this is row 2. The vertical alignment are called columns.
How many columns do we have here?
3. Column 1, column 2, and column 3. Column 1, column 2, and column 3. The size of a matrix, it's not the size of a room. If you're going in to buy a carpet in well, who would want to buy carpet, okay? But you don't look at a square or a rectangle and say, oh, the size of that rectangle is 7. What you do is you give its dimensions. That's what you do for a matrix. For the size of a matrix, you give its dimensions. It's the number of rows by the number of columns. So for this matrix I made up here, we would say that this is a 2 by 3 matrix.
And that little X is read as by, just like when you talk about
the dimensions of the, say, the floor in a room. It's 22 by 17 feet, something like that. The size is given 2 rows, 3 columns. And there's a special type of matrix where the number of rows is equal to the number of columns. We don't have that in this example here. But if the number of rows is equal to the number of columns, I bet you can help me figure out what these things are called. What do you call a rectangle where the vertical distance and the horizontal distance are equal? Suppose you have a rectangle that's 5 by 5 or 7 by 7. What do you call that rectangle? Starts with an S. Square. Okay, so if the number of rows is equal to the number of columns, that's called a square matrix. And it's going to be important because when we start finding determinants in a few minutes, you can only find the determinant of a square matrix. An augmented matrix summarizes the coefficients and the constant terms of a system of equations. An augmented matrix, it's going to take me longer to write out this definition for augmented matrix than to show you what it is. It summarizes the coefficients, coefficients and constants in a system of equations.
And you know what? I'm just shocked that I hadn't mentioned this already. Those problems 1, 2, 3, 4, 5, where we had the two equations, that's called a system of equations.
I said it at the very beginning.
Oh, okay.
Two equations, and solving a system is finding a point
okay. I
of
wasn't paying
intersection.
attention to you. Okay.
At least I said solving a system of equations is finding a point of intersection. So I recall saying that. But a system of equations is just two or more equations written together. So let's not make this any harder than it already is. For the augmented matrix, question.
Can I just copy down the stuff that I
Oh, I'm sorry. Here. Okay. Let's see.
Trust me, writing down what I'm writing is taking longer than.
Yeah. You do a good job of making a short topic long.
But I'm still talking faster than you, okay? So you notice I'm trying to talk faster because I know this is a long assignment and we're trying to get through the whole thing. All we have to do is with augmented matrices is set them up and interpret them. So we're not going to do that much with augmented matrices. Most of the matrix work that we're going to do will involve determinants. You'll see that in a moment.
That's what we should say there.
All we're doing with augmented matrices is setting them up and interpreting them. Notice to set up an augmented matrix, it's just like elimination. You need the like variables already aligned. We have that. We need the constant terms on the other side of the equal sign. We have that. So the first column in the matrix is going to summarize the x coefficients. So the first column, we have a -5 and a +5. What will we have as the second column of the matrix? 7 and -5.
And do y'all see the little bitty vertical line?
That vertical line is taking the place of the equal sign. That's saying you're moving to the other side of the equal sign. So
that's the column of constants.
This is the column of constants, which is going to be 1 and 7. Oh, no. Oh. 1, click. I bet if I tabbed it would have done it. And 7. Oh, check our answer. Oh, I thought they asked for the size of the matrix.
They quit that.
Oh, they quit? Well, if they had asked for what size, what would be the size of this matrix here?
2.
There'd be another 2 by 3. There's 2 rows and 3 columns. Oh, here's another one.
Are all the variables lined up? Yeah. You have an X column, a Y column, a Z column. All the equals are lined up. And on the right, you have the constant. So
let's fill in the X column. We have the coefficient 2 7. Hey, wait a minute. I don't see an x term in the third row. What's the assumed coefficient for x? And don't say 1, because if it were 1, you'd see the x. I don't even see an x.
How many
there.
x's do you see here?
0. The coefficient is 0. You call out the second column, the coefficients that are in the y column.
Oh, -2. Are you telling me to call it out?
No, I'm telling them.
Oh, okay. -2.
-8.
They said they wanted me to call it out because we're the only two people here having a good time. 5. To them, it's just work.
Oh, okay. And now I'm going to let the students call out the column for the z column, the coefficients for the z column. 2, 6, and this has to be the easiest thing we've done this semester, just setting up augmented matrices. The column of constants, we move to the other side of the equal sign. -1, 6, -7. I agree. And if they'd asked for the size of this matrix, what would it be? How many rows do we have? How many columns? So this is a 3 by 4 matrix. Now we have to interpret. They ask us to interpret the augmented matrix. I'm going to write this one down, okay? Give me a moment.
Okay.
This is number 8.
You basically, in algebra, you always do it one way, and then what do? Reverse? Isn't that what we're doing here? Here you're given the matrix, and now you got to fill in the equations. So,
And we have a vertical bar, and that is 9, -6, 8. Okay, switch over to my, well, let me make sure I didn't miscopy. Yes, okay. Oh, and notice down here, they want us to come up, we're going backwards. We have the augmented matrix, we're writing the system, and they're telling us what letters to use down here. We're going to use X, Y, and Z. I could just as easily have said use A, B, C, or P, Q, R, but we're using X, Y, and Z. That means the first column is the coefficient of X. The second column are the coefficients for Y. The third column are the coefficients for Z. And that green vertical bar is interpreted as equals, good. So we say 1x, and that's a positive 9, so plus 9y, and that negative is interpreted as a minus 9z equals 9. Tell me what that second row is saying in terms of an equation. Okay, so we have 0x, the x is gone. We have an 8y, keep going, minus z equals -6. They may want us to write them minus 1z. I'm not sure. We'll have to see when we're typing in the answer. They may want us to show the 1. Third row, 8x plus 9z. We have no y in the third row equals 8. Has to be the easiest thing we've done so far. Here's the system of equations associated with that augmented matrix. So let's look over and see. X, that's a plus 9. Oh, they already have the minus sign there beside. No, that's right.
Okay.
Plus 9y. And now, don't write a -9. I thought you had to put in the sign also, but no. Just the 9. What's going to go? Okay, that's a 9. What goes in front of the y on the second equation? 8. And there's a -6. Third equation?
Oh, I don't like the way this isn't
Oh,
lining
they're not
up.
aligned.
Okay,
I don't
well,
like that. I'll complain to the people at Pearson, and eventually they'll get it lined up. They do listen to the teachers, okay? Unfortunately, sometimes they listen to teachers, and I don't agree with the changes they made, but
squeaky wheel gets the oil.
yeah, remember that, the squeaky wheel
Young
gets the
enough.
oil.
The person that complains loud and stuff,
Now, there's something, how many of y'all are business majors? Do we have any business majors here? If you did, you'd probably have to take the math for business, and in that course,
you're going to see some great applications.
we take these systems of equations that look at these augmented matrices. We'll take systems of equations, divide it as an augmented matrix, and then we use something called row reduction to rewrite the matrix so it looks like, let's look at number 9. Look at this. They've given us an augmented matrix. So let me write this down.
Oh, I think we can do this without writing it down.
Oh, you're right.
It says, write the system of equations. Do not solve. Well,
Realize in Math 1324, we go through and we take augmented matrices that look like this thing here, and we get it so that we have ones down the diagonal and zeros above and below. It's not an easy, quick thing, okay,
unless
to
you're
get that
using,
done. Unless you're using a calculator to do it. But if you're going through it by hand, it's not an easy, quick thing to do. But we can use row reduction to get ones down the diagonal and zeros everywhere else.
That's how you really want a matrix written.
Because what does that first row say? Once it's written like this, what does that first row say? They tell us to use X, Y, and Z. I could swear they used to say A, B, and C.
Well, now they say X, Y, and Z.
What does that first row say as an equation? We have a 1x, which is just an x. X equals 6. So by getting the equation in with the ones down the diagonal and zeros, the matrix, with the ones down the diagonal and zeros above and below it, that's called reduced row echelon form, by the way. We know that x value is 6. Now look at the second equation. What's it saying? Y is 1. And the third row? If you can go through using that matrix reduction to get ones down the diagonal and the constants, zeros above and below those ones, then the constants on the right-hand side, that's the solution to the system. That's the point, or in this case, that's the point of intersection.
And we're now through with augmented matrices. And we're going to do something
called determinants. A determinant, switch over.
With determinants, it's got to be a square matrix. Is this a square matrix?
How many rows do we have? 2
rows.
How many columns?
2
okay.
Columns. Okay. Lift up your
so I'm just now, let's see. We're going to look at, first of all, a determinant is a unique number assigned to a square matrix. I don't know why I'm writing that out. It's a unique number assigned only to square matrices. I'll say assigned to a square matrix. Now, normally we enclose a matrix in those brackets. Go back, let them see and compare the notation. Look at number 9. Go back to that matrix there.
You see it's enclosed in square brackets.
You see the little hooks on the top and bottom? They're brackets. But to represent a determinant, we use big absolute value bars. If you take a linear algebra class, it turns out that the properties of absolute value can be applied to the properties of determinants. Something like the triangle inequality of absolute values there's a triangle inequality for determinants, but that doesn't matter
For
to us.
y'all.
All you have to remember is that if you see a rectangular arrangement of numbers and they're in a big absolute value bars, that means find the determinant. The first thing we're going to do is look at a 2 by 2 determinant.
So it's going to state the formula, if you will, for finding a determinant
Of a 2 by 2 matrix.
A 2 by 2 matrix would have
2 rows and 2 columns.
So it's 4 numbers altogether. Hey, using the letters A, B, C, D, if I asked y'all what's the first number up here, what would y'all say the first number is? A, B, C, or D?
A, you start at A. You start there. Loosely speaking, or if you're going to describe it in words, a 2 by 2 determinant is the difference of the cross products if you start up there at the row 1, column 1 position. It's AD minus BC. Don't make 2 by 2 determinants harder than they are.
A common mistake is people will do BC minus AD. No, you gotta always start with the first number. If you reverse it and get BC minus AD, you'll get it wrong every time. So you just multiply
minus multiply.
Okay, not hard.
Look at the
okay, write down number 10.
We want to find the determinant. And determinants give us a very nice method for solving systems of equations. That's why we're looking at them right now. But 3 negative 1, okay, switch over. You multiply, you start at the 3. 3 times negative 4 is negative 12. Minus.
That's the minus right here.
That minus is the minus from the formula. Negative 8 times negative 4 gives me a positive 32. Negative 12 minus 32, is that a negative 44? So the determinant for that matrix is negative 44. Once again, not too difficult. Any questions there? Do we have another 2 by 2?
Let me type it in. Nope. You'll see another 2 by 2 when you're doing Cramer's rule.
Okay.
Now, the next one, that's a 2 by 2 matrix. And what we just did is something called crisscross.
We're using the crisscross method. And there's a crisscross method that can be applied for 3 by 3s as well. Notice a 3 by 3, that is 3 rows and 3 columns.
Now this one's going to take a lot of crisscrossing.
Let me write out the formal definition first, okay? All right, switch it over. Okay. You have your vertical bars, and there's 3 rows and 3 columns.
Oh.
So A, B, C, D, E, F, G, H, I, and realize that E is not the natural exponential.
Not 2.7.
The I is not the square root of negative 1. These numbers are all just real. These letters are all representing real numbers. And here goes, okay? There's more than one diagonal. See if y'all follow the pattern. Left parentheses. It's A times E times I plus B times F times G plus C times D times H. Close parentheses minus.
Oh, we should have started writing there because
Okay. Now, we have three other diagonals. Inside the second set of parentheses, it's a C times E times G plus A times F times H plus a B times D times I.
It looks, if you're thinking that, do I have to memorize this?
Do y'all see
No.
the pattern? Did y'all see the pattern?
It's a crisscross pattern. It's a crisscross from, well, let's say it.
Okay.
I think if you
Recopy that's the trick. Recopy the first two columns. Don't worry about these letters here like that. You need to see the pattern. Recopy the first two columns.
Write down the whole problem.
I'm writing it down. I am, Tony. So, A, B, C. So, when you run into a 3x3 matrix, the first thing you do, recopy the first two columns right here to the right of the matrix. That's an ADG and a BEH. And with the determinant, you always start in the A position. Always start at that first number that's written. You move down the diagonal. A times E times I. There's that product. B times F times G. There's the second one. C times D times H. There's the third one.
So multiply, multiply, multiply.
And then minus. Now you're going to find the products from, let's see, I think I'm going to use, I'll use the purple. Now you're going to go the opposite direction. You left off here at C. C times E times G. A times F times H. B times D times I. It'll look better when you have numbers in there, okay? There are three diagonals falling from left to right, minus three diagonals falling from right to left. You always start in that A position.
If you do the CEG first, if you go this way first, you're going to get it wrong every time.
You'll get the sign will be wrong.
Just
like if you do it.
And if you get the sign wrong, Pearson's going to say wrong. They're not going to say we have the wrong sign. Just like if you do it
reverse here, you're going to get the wrong sign.
Always start with that first. So recopy the first two columns, and then it's crisscross, 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 minus
crisscross, crisscross, crisscross. Let's look at number 11.
Oh, shoot. There's not a lot of... I like it when there's a lot of zeros in the matrix, but at least there's a couple of ones.
Why would we say we like it when there's a lot of zeros? Anything times zero is what? Say zero.
It's going to get you smaller numbers.
This reminds me of when Jeb Bush was campaigning and he asked the people there to please laugh. He made a joke and no one at the campaign rally laughed. That reminds me of when he asked the people to please laugh. So, okay, 1, 3, 5. Okay.
This is one of those times I check the numbers twice to make sure. Because
you write it down wrong, you're going to...
Yeah.
Oh, goodness. Oops. Okay. So, switch to my paper. The first thing you do, recopy the first two columns. 3, -4, 2, 1, 3, 5. We're going to have parentheses minus parentheses. And here we go. 3 times 3 times -8. 3 times 3 is 9. Times -8 is -72. Move over to the next one. 1 times 1 times 2. That's a +2, a +2. The third one, 3 times -4. 2 times -4 times 5. Thank you. That is a negative 40, so minus 40.
That's what we did. Multiply.
Multiply. Now we're going to go in the opposite direction. We're still positioned right here. We're just working our way across this big tableau, this big arrangement of numbers. We're still positioned there at that 2. 2 times 3 times 2, that's a positive 12. 3 times 1 times...
Wait, are y'all caught up?
Yes.
What's the next number he's about to write? 15? Okay, good.
And here, what am I going to write? Okay, be careful. Negative times negative, that's a positive 32. And I'll see people that go through and distribute the minus. I don't do that. I simplify. First of all, let's simplify inside the first set of parentheses. Negative 72 plus 2, that's a negative 70. Minus 40, I'm getting a negative 110 minus that red minus from the formula. Now work inside the second set of parentheses. 12 plus 15 is 27. 27 plus 32, is that 59? Negative 110 minus 59, is that giving me a negative 169 for the determinant? Agree or disagree? Yes? Okay. Let's see if I'm right. We'll punch it in there. Okay. Let's do another 3 by 3.
Oh, I like this one. Zeros. And you'll see why. I just think it's a little easier when there's a lot of zeros, because
0 times anything
is 0.
is 0, yes. Rewrite the first 2 columns. 10, negative 1, 9.
Oh, wait, let me show what you're doing.
10, negative 1, 9. Negative 3, 9, 2. We're going to have parentheses minus parentheses. And we start up here, row 1, column 1, 10 times 9 times 0. 0, that's why Tony said he likes those zeros. Move over, negative 3 times 0 times 9. Another 0, so we have 0 plus 0. Suppose we have a whole column or a whole row that's 0. What do you think is going to happen? If we had 0 for an entire column or an entire row, that would be nice because our determinant would turn out to be 0. But here it's not to be 0 because this next diagonal doesn't have a 0. 3 times negative 1 times 2 gives me a negative 6. I agree. Now we're going to go the opposite direction. 3 times 9 times 9. 9 times 9 is 81 times 3. Is that a 243? But what are the next 2 cross products going to be? 10 times 0 times 2? 0. Negative 3 times negative 1 times 0. So we have, simplifying inside the parentheses, we have a negative 6 minus, the minus is from the formula. The second set of parentheses is just a 243. Negative 6 minus 243 is
negative 249.
Okay. Tony, from now on, when you're going to answer the question, I want you to change your voice so that it isn't so obvious that you're just answering the question for me, okay?
I can be like Katie at the cattery. I can't believe she can do all those different voices.
I was wondering, does she have an app? That's
I don't know, but she did it there.
I know.
On the video, and so
it had to be true. I mean, it has to be real because you saw it on TV. I mean,
it
on
wasn't
the
on
phone.
TV. It was on my phone. Okay. Negative 249.
And now,
having done that, they need to remember, before we do number 13,
you have to remember how to find a 2 by 2 determinant. That doesn't have all those different cross products. It's just cross multiply minus cross multiply. The 2 by 2 determinants are the quick ones, okay?
And that's what we're going to be using now, starting with problem 13.
Cramer's rule. Let me tell you what Cramer's rule
Let me just show them the example. It says solve using Cramer's rule. Do we know have we seen other methods? Well, yeah.
Elimination and substitution. But Cramer's rule really is best for solving this. But once again, if you said, I'm going to multiply that first equation by a -3 to get a -6y and use elimination to solve it, I wouldn't know. Because elimination, substitution, and Cramer's rule all give the same answer. But Cramer's rule is so nice. It's all numeric. There's no variable manipulation involved, and it's very easy from a computer programmer point of view. This process is very easy to solve systems of equations. So this is number 13.
So this
I didn't write it down.
Oh, I thought you were going to write something about Cramer's rule.
Oh, yeah, you're right. Okay, Cramer's rule.
Cramer was a famous algebraist, a mathematician in his day, and he'd probably roll over in his grave if he
knew that this little thing is the thing he's remembered for. He did so much high-level math, especially in the area of linear algebra and matrices. This is the thing he's remembered for. It uses determinants to solve systems of equations.
By the way, in any English language math book, DET is universal for determinants. That's a universal abbreviation in English. Okay? So if you go pick up a Russian textbook, they're not going to be using DET for determinants.
It uses determinants to solve systems of equations, and Tony likes to write out a sequence of steps, but I'm not a sequence step writer.
Just write out x equals dx over d.
I'll do that later. Okay, right now, I'm going to go through Cramer's thought process with them, looking at an example. Let me see that problem. This is number 13. We want to solve this system of equations. So at this point, once you master Cramer's rule, you'll have 3 different methods that you can use to solve systems of equations. You have elimination and substitution. This next one is Cramer's rule. What Cramer is remembered for, he's mentioned in every algebra book there is, for this little rule for solving systems of equations. The first thing he did was he just ignored the constants. Let's find the determinant of the coefficient matrix, okay? So we call that D for determinant.
Called capital D, the determinant of the coefficient.
So you have to make sure you have your X's and Y's aligned, which we do. The first column would be 3, 8. Those are the coefficients of X. The second would be 2, 6, the coefficients of Y. And we know how to do this. This is one of the short determinants. You just crisscross. Cross multiply. 3 times 6 is 18. There's my blue pen. 18 minus, remember this red minus is from the formula, 2 times 8 is 16. 18 minus 16 gives me a determinant of 2. D is equal to 2. He then formed, is everyone caught up? He then formed the determinant of the matrix that he called D sub x. D with the subscript x. That's the determinant you get when you replace the x column with the column of constants. So instead of 3, 8, we have a 6, 5 here. The second column is still the 2, 6, the y column. The determinant, when you replace the x column, you go to D, you replace the x column with the column of constants. Let's see, that's a cross multiply, so 36 minus cross multiply, that's a 10 to give us a 26. And he found these subscripted determinants for every variable. There was an x variable, he found d sub x. He then found d sub y using that same pattern. D sub y equals, each time you go back to D, the x column is back to being 3, 8. The x column is back to 3, 8. The y column, now he's replacing the y column with that column of constants, 6, 5. You don't leave the x column 6, 5 and then do the y column 6, 5 as well. If you have two identical columns, the determinant's going to be 0. That's not what you're doing. You only replace one column. Whatever the subscript is, that's the column that's being replaced in D. So that's cross multiply 15 minus 48. 6 times 8. 15 minus 48 gives me a negative 33.
And now here's the thing that, if someone said state Cramer's rules, write it out.
Here it is. He was able to prove that x, the x value in the point of intersection, will always equal d sub x divided by d, and y will always equal d sub y divided by d. If there had been a third variable z, it would be d sub z divided by d. But that would have been one of those big determinants, the 3 by 3 determinants. We're only making you use 2 by 2s here for Cramer's rule, but it can be extended to a 3 by 3 determinant, or to a system of equations with 3 variables and 3 equations. So, using Cramer's rule, these lines are going to intersect where the x value is, what was d sub x? 26 divided by, what was d? 2. 26 divided by 2 is 13. So these lines up here, they're going to intersect where the x coordinate is 13. The x coordinate is 13.
What's the y coordinate going to be?
D sub y is negative 33 divided by, that you better not mess up on d, because you use d for both the final answer for x and y. So you better make sure d is right. D is 2. Hey, can we reduce that? Negative 33 halves? No? There it is.
It really, I know it looks sort of messy, but if you're going to bind it with fractions as answers,
This is the way to go.
because you get the fraction right here, but you don't have to do anything with it. It's not like you got to plug it in or anything.
Notice we didn't move any variables around. It's all numeric. This is all numeric. Multiply minus multiply. We didn't combine like terms somewhere, get all the constants on one side, the variable terms on the other. It's all numeric calculations. That makes it very easy to program. I remember in a class for, it was called programming for math majors, but Tony and I were the only math majors in the class. The rest of the people were business majors, taking it as an elective. And here's the funny thing. The teacher was a business computer programmer, okay? So this person's math knowledge wasn't that great. The first day of the semester, the teacher goes in and says, okay, write a program using, I think we're using Pascal to some of those dead like programming languages, and to solve a system of equations. And people were going using elimination and substitution. I remember Tony and I both said, that's crazy, use Cramer's rule. It took like 4 lines of code total. That teacher had never seen Cramer's rule.
And he tried his best to give us a 0, that we were cheating somehow.
And then he uttered the immortal, I had my linear algebra book. Here it is, Cramer's rule. It's a real method. Why don't you call the head of the math department and ask them if they've ever heard of Cramer's rule? Well,
that's when he said math
majors just have an unfair advantage in this course.
And we were
Little did we know, sitting in that course was a student that was minoring in journalism and worked for the school paper. So we got a picture of the teacher, and then on the headlines, there it was. This is back in the 80s.
Let's see. Teacher says math majors have an unfair advantage in course entitled Programming for Math Majors. So, he never liked us. That teacher did not like us, and
did everything possible to ruin our 4.0 averages. We made A's in the class,
but okay, let's do another one just to make sure. Then we're going to get to the word problems, and this is going great.
Okay.
Oh my gosh.
Hi, Tatiana. Tatiana's already done the assignment. Let me write this down. 8x plus 8y is equal to 8. And 9x plus 8y is equal to 5. Once again, we're going to use Cramer's rule. We switch over. Notice the like variables are already aligned. We have the x's aligned, the y's aligned. We have our constant term on the right-hand side. So the first thing we're going to do is find the determinant of the coefficient matrix, just D. That would be the coefficients of 9 are 8, 9. For y, 8, 8. So we multiply.
64.
You're supposed to change your voice.
Oh, yeah.
64 minus 72. Good. And that gives me a -8. And remember, the way you divide by this, you better make sure your D value is wrong.
It's right.
It's right. If it's wrong, make sure it's not wrong. If it's wrong, then your X and Y's are going to be wrong too. Now we'll find D subscript X. Call out the first column to me. 8, 5. We're replacing the X column with the column of constants. What's the Y column? 8, 8. It's the same as in the original matrix. Then we multiply. 64 minus, 8 times 5, I'm getting 40. 40. 64 minus 40 gives me 24.
How long do y'all think it took him to figure this out, to come up with this? I guess that's why he deserves his name mentioned. I don't see how, and I think it would have taken a while for him just to,
Even think of it.
right? Don't you think so?
I remember seeing, I mean, we proved it, we derived it in linear algebra, but. Okay. First, now we're finding d sub y. What's the first column in the d sub y determinant? Okay, good. It goes back to the original values, 8, 9. The y column is 8, 5. So we multiply 8 times 5 is 40 minus multiply and 40 minus 72 gives me, okay, and so according to Cramer, x is equal to d sub x over d, so 24 divided by negative 8, which gives me a negative 3. That means that these two lines are going to intersect at an ordered pair where x is negative 3, y is equal to d sub y divided by d. D sub y is a negative 32 divided by d is still a negative 8, which gives me a y value of 4.
It's sort of unfortunate that we're not getting strange fractions, but looking at last semester, there was one, let's see, where are the answers? X is negative 3 over 2, Y is 3 over 2. Well, if they'd been fractions, they'd make this seem better because, oh, wow, you didn't have to do anything. Different, okay?
Yeah.
But here we're getting integers, but it might turn out, when you do it, yours might be a fraction, okay? Any questions on that? Oh, wait, I better put in that answer. Oh, wait, what did I just do?
Uh-oh.
There. Print. Make sure you put these parentheses, by the way. Negative 3, 4. Any question there?
Any questions?
Because we're now going to hit the word problems.
Let's start at number 16.
I think 16 is a better one to show the pattern on how to set these up. Tatiana had already done this, and she said, she liked the tables that we're using to set these up. So let's move to number 16. And then we'll go back to 15, but I just thought 16 looks out a little bit nice. Oh, we're switching. Oh, okay. A woman bought some large frames for $19 each and some small frames for $7 each at a closeout sale. These are picture frames.
Are they? Okay.
I guess. If she bought 17 frames, what the heck is she doing with 17 picture frames?
If it's picture frames, she owns an art gallery.
Art gallery, okay. She bought 17 frames for $167. Find how many of each type she bought. Okay. When doing these word problems, you're going to have to summarize the problem. The first thing I ask myself when I'm looking through this problem is, okay, what are the unknowns? What are we trying to find?
And notice how we keep going back and rereading the problem.
The woman bought some large frames and small frames.
I think this question or this statement here.
Find how many of each type she bought.
I think that's what we don't know. The number of large frames and the number of small frames.
And they even give you a hint with that first little question there. She bought blank large frames. Flip it. I'm going to start summarizing this stuff like this. I'm going to first write out, what are we trying to find? We want to know how many large frames she bought, and how many small frames. When we set this up, we're gonna try to come up with equations that look like this.
Oh, and one thing that you'll notice is to have a unique solution, switch back. Generally, if you have two variables, you want two equations, two unique equations. And so we have switch over back. There are two things we don't know. That means we're going to have two variables. We better come up with two equations. The first column, well, we don't know the quantity. I'd say X and Y and label that quantity. There are X large frames and Y small frames. How many did she buy? Quantity is shorter than writing out how many. So, but if you want to write how many,
for all of these word problems, you start off figuring out what are we trying to find, and then identify the variables. X is the number of large frames, Y is the number of small frames.
Let's go back and read more of the problem.
Okay.
I'm going to read it again. They're telling us the cost per item. The large frames cost $19. The small frames for only $7. I think we better summarize that on the table.
I'm going to label a column called cost. And what did it say? The large frames cost $19. The small frames cost $7.
I put the little dollar sign in front of both of those.
Okay. Now, if we're going to write equations, we've got to have equals, okay? So let's look back at the equation.
Maybe they gave us some totals. What do you think?
Did they?
I think they did. She bought a total of 17 frames. And they even gave us the total amount she spent, $167.
Is that 17? Let's do this 167 first. Is that $167? Is that a total quantity or a total cost? Cost. I like you putting the dollar sign. You are going to put all of the dollar signs should be in the same column.
I thought it was 169. Was it 166? Yeah, you're right. Okay.
No. How many? What's the total for the quantity?
How many frames did she buy? Total 17. So we're going to total that quantity. The total of the quantity better be 17.
And if you read vertically, you have the two equations. What do I mean by that? Well, if X is the number of large frames and Y is the number of small frames,
if you add those two numbers together, X plus Y, they better give you 17.
Here's my first equation. X plus Y equals 17.
Now for cost, let me ask you something. Suppose she bought 10 large frames. Suppose X was 10. How much money did she spend on her 10 large frames? If she bought 10 large frames, how much money? Well, it couldn't be 10, okay, but 10 large frames would cost how much? 190. You take the cost per item times the number of items. Each large frame costs $19 times she bought X frames, so 19X. That's all the money she spent buying large frames. Let's add all the money she spent buying small frames. Each small frame costs $7. The cost per item times the number of items. That's 7Y. So 9X is how much you spent on the large frames. 19X is how much you spent on the large frames. 7Y is how much you spent on the small frames. Adding that money together, it better equal the total amount of money she spent, $167.
Now, at this point, it's up to y'all. Elimination, substitution, or Cramer's rule. I think I'm going to use elimination. I think that this is, it's not, I can't just add vertically. I get 20x and 8y. So I wouldn't do it like that. But there's something I can multiply this top equation by. Well, if I wanted to eliminate the x, I would need a negative 19 right here.
But negative 19 times 17, that's getting mighty big. I'd eliminate the variable that has the smaller coefficient. So the y's, to get a negative 7, you see what I would do is I would write it like this. I'd put the negative 7 right there. We're going to distribute through a negative 7 on that first equation.
Why are we doing this? Because now I think we can eliminate those y's. Let's see, what's 17 times 7?
Is it 119?
Yeah, it'd be 70 plus 49, so negative 119.
Might be a good idea. Oh, we don't have a... Oh, the day they brought in the new computer, I came in and put the little VI thing on there, but it's never been used. Oh,
is this something we can now solve with elimination?
I don't know. I guess I'll just say next. Oh, okay.
This is the elimination stuff. Do I need to jog y'all's memory of, should I have done that before? Y'all forgotten about the elimination, the way you add it vertically?
I'm just going to...
So negative 7x plus 19x, is that going to give me a 12x? By the way, on this problem, would it be okay to get a fraction? No.
Or a negative number?
Oh, a negative number?
Certainly not. Okay.
Let's see, negative 119 plus 67. That's going to give us
48?
A positive, what?
48.
48. So we have 12x equals 48. Divide both sides by 12.
To give us x
equals what? 4.
So what is that x representing? Large frames. She bought 4 large frames.
I like to come over here and put another column on my table called answer. What am I going to write right here for large frames? Well, 4. She bought 4 large frames. Now you can either do algebra or just logic your way through.
She bought how many frames total? 17. 4 of them were large. So how many small frames did she have? It had 13. To be 13. Mm-hmm. 17 minus 4.
Now if you want to do, algebra and say, 4 plus y equals 17, subtract the 4.
You still get y equals 13.
That's what I like to just think the way through there. Okay, if she bought 4 large frames and she had 17 altogether, that means she bought 13 small frames. Any questions there?
Okay, so she bought 4 large frames and 13 small ones.
What did 15 last? We'll come back to 15 in a moment. Let's do 7.
15 is easy. It's just these talking about the 2-point points and
Tatiana said that the frames, that was the best example to do first. Okay, so
the cost to attend a movie is $11 for adults, while children are admitted for $8. If a movie was attended by 59 people who paid a total of $514, how many adults and how many children attended the movie? So let's reread it. The cost to attend a movie is $11 for adults and $8 for children. We know that 59 people went to the movie, and they paid a total of $514. How many adults and how many children attended the movie? What are the unknowns? What do we not know here?
And it should be obvious. Move your mouse right there. It's saying it. right there. How many adults and how many children? So what am I going to, instead of large frames and small frames, what am I going to write? Adults and children, good. Are you going to let them see
And we
what
want to
I'm
know
writing?
how many adults and how many children.
Oh, you're letting us.
So X and Y are the number of tickets. I'll just say quantity.
Yeah,
Just say quantity again. How many?
I think there's even going to be a cost column.
Let's see. Tony, I just remembered something. I have to tell you right now. Okay. So
what are we going to put in my cost column? Well,
adults cost $11 each, and the children
11 and 8.
Okay. We need some totals. We're trying to come up with, we have two variables, so we need two equations.
So these equal lines for my totals. What were those totals? What was the total quantity? How many tickets were sold, or how many people attended?
59. Okay. So totaling up the quantity, 59 tickets were sold. Now,
how much money did they bring in? 514.
Hopefully you see the two equations.
Hopefully you're thinking, oh, this is sort of like number 16. The setup is?
What's the first equation? Okay. X adult tickets plus Y children tickets better give us 59 total tickets. So the quantity equation is X plus Y equals 59. What's the cost equation? How much money was spent on the X adult tickets?
Suppose only 5 adults went there.
How much money did the theater make if there were only 5 adults? 55. It's the cost per item times the number of items. So 11X, that's the amount of money that was spent on adult tickets. How much money was spent on children tickets? Cost per item times the number of items, so 8Y. Here's the money they took in from the adult tickets. Here's the money they took in from the children tickets. Combined together, it better give us the amount of money they took in from all the tickets, $514. Any questions on our logic there?
No.
Do y'all have a feeling one way or another? Was there anyone passionate that would rather use substitution or Cramer's rule? We could use Cramer's rule. The products would get sort of big because the constants are big.
Yeah.
But unless there's someone really wanting to use a different method, my preferred method is elimination. So I'd recommend. What do y'all want to eliminate? Do y'all want to eliminate X or Y? Better question is, what variable do you think your teacher would eliminate? Y, because 8 is smaller than 11.
Yeah.
What are we going to have to multiply that first equation by if we want to eliminate Y? A negative 8. I agree.
So we would have a negative 8X and a minus 8Y equals, what about 59 times negative 8? Ooh.
But let's see, 50 times 8 is 400. 9 times 8 is 72. So negative 472.
If you have a calculator and doubt it, you can check it. Or you can punch it in. 11x plus 8y is 514. Draw an equal line. The y's are gone, aren't they?
You've eliminated the y's.
So negative 8 plus 11x. Is that going to be a 3x? Equals negative 472 plus 514. I sure hope we're going to get a multiple of 3.
How about a 42?
Okay. If it's not a multiple of 3, we can't have a
fraction of an adult ticket sold.
Uh-huh.
So we better get a non-negative integer.
So,
and 42 divided by 3, 14. So come up here to your table. That says there were 14 adult tickets sold. Well,
okay, how many children? Well, there were 59 altogether. So I will write out my logic on this one. The number of children would be 59 minus 14.
so
45 children attended them. So there were 14 adults in the theater and 45 children.
Oh, wait, no, I'm coming over here. 14 adults. And what do you say, 45 children?
Mm-hmm. Okay. Mm-hmm.
Oh, use Gaussian elimination or Gauss-Jordan elimination. That's the stuff where you get the ones down the diagonal and the zeros. We're not doing that. Use either elimination, substitution, or Cramer's rule. Ignore those instructions. Okay? So don't view an example.
Yeah.
I like the problem, I just don't like the instruction. You should have put in an instructor tip here saying use elimination, substitution, or Cramer's rule. Preferably elimination or substitution.
Oh gosh, poor Mike.
He works a total of 61 hours per week at his 2 jobs. He makes $8 per hour at job A and $9 per hour at job B. If his total pay for 1 week is $509 before taxes, then how many hours does he work at each job?
So I'm not going to go with large frame, small frame, or adults or children. What am I going to start off? What are my unknowns? Yeah, how many hours at job A and job B? So I just write job A, job B.
I still prefer using X and Y, although we could use A and B as the variables. Y'all want to do that? Hey, you want to use A and B? Oh, okay.
Quantity.
So, he worked X hours at job A. He worked Y hours at job B. Let's go back. What else do they tell us? He makes $8 per hour at job A and $9 per hour at job B.
So instead of cost column, I think I'll call this his pay column?
Yes. Pay per hour.
Say pay. So how much did he make per hour at job A?
8. And job B, it was $9. Okay.
Flip back. I mean, there's a lot of flipping back and forth on this.
Okay. If his total pay for 1 week is $509, and we already know he worked a total of 61 hours. They told us that. Let's deal with that 61 right now. Let's look back at the table.
Where am I going to put the 61 hours? Yeah, under quantity. And I forgot, how much was that pay of his?
509. We have 2 variables, so we need 2 equations. Y'all see the equations?
It's just so,
give me the quantity
this
equation.
Is something you see a lot of in business math. There's so many applications of this. These little tables like this can set up.
When there's there's a job C also. And there's more than.
So we have x plus y is 61. And
suppose he worked 10 hours at job A. How much money did he make from job A?
8 times 10
so
is
$80. So it's the pay per hour times the number of hours. 8x is all the money he made at job A. And 9y, that's all the money he made at job B.
Well, I'm going to use elimination.
What letter do you think we're going to eliminate, X or Y?
Yeah, I'm going to eliminate X. I'm going to do the one that's smaller.
So what's he going to multiply by? Negative 8. Remember, he wants the same coefficient but the opposite sign. So he has a negative 8x.
Then a minus 8y is a negative, 60 times 8 would be 480. And then 1 times 8, is it going to be 488?
So.
And we copy the other one. And this is going to work out really nice, isn't it? And I add vertically. The 8x's are being eliminated. Negative 8y plus 9y. That's just y equals 21. Now be careful when you write that answer column. Where you write the 21 really matters. You need to make sure you're writing it on the what? Job A line or job B line? Job B.
Y is the number of hours.
So maybe I should have used A's and B's instead of X's and Y's. But so altogether he worked 61 hours. So could we figure out how many hours he worked at job A pretty easily? What would it be? 40. I'll just say 61 minus 21. Poor Mike working a full-time job and then 21 hours at job B and making only $509 before taxes. The phrase before taxes, that's one of those things that at first I'm sure they didn't have that phrase and someone told them, some teacher said, put on there before taxes, because, who gets a job? I guess if you're paid cash. Yeah, okay. Well, still, so punch in the answer. 40 for job A and 21 at job B.
So he worked 40 at job A and 21 hours at job B.
This little pattern can be used even if it's not dollars and cents. Let's go back to the one we haven't done, number 15.
There's no review material on this assignment, but you have a lot of reviews ahead of you, okay?
Review for quiz.
Review for the final exam. So there's plenty of reviews for you. But there's not a review problem, so it's all new material. Number 15, a basketball player scored 22 times during one game. He scored a total of 36 points, 2 points for each 2-point shot, and 1 point for each free throw. How many 2-point shots did he make? How many free throws did he make?
At first glance, you're like, there's no dollars. This is a different, it still sets up the same way. This little pattern that we have is this table. It can solve infinitely many word problems, or at least set it up for you. Okay, so instead of job A, job B, large frame, small frame.
What are the unknowns?
Did you hear that too? How many 2-point shots?
I think I'd like this problem better if they called them 2-point shots and 1-point shots. It's the fact that the names are so Okay, one of them's a 2-point shot. The other thing is a free throw.
Oh, Tim.
You're
It's
right.
okay.
And
So we want to know how many of each. So is there still going to be a quantity column?
okay.
Yeah. So X and Y.
X is the number of 2-point shots. Y is the number of free throws.
Now there's no money involved here. There's not
But
going to
there
be
is something per throw. Let's see. For each 2-point shot, he scored 2 points. For each free throw, he only scored 1 point. So
instead of a pay column, maybe a point column.
So the 2-point throws, he earned 2 points for the team. The free throws, he earned 1 point for the team.
Now let's look at the problem and figure out the the totals.
A basketball player scored 22 times during one game.
He scored a total of 36 points. Here it's not that it's not like dollar signs. So, it's going to be the dollar sign.
Mm-hmm.
Okay, but what are the two totals going to be? The 22, is that a quantity or is that the points?
The 22, where are we going to put that? Is that the quantity, a total of quantity, total of number of shots, or a total of points?
Well, yes.
The quantity. He scored
Maybe
X 2 points plus Y free throws, so he scored a total of 22 times.
If
this is just the number of times the ball went in the basket.
Look at the number, 36. It says 36 points.
That's a total of points. You're totaling the point column there. Any questions on our logic? X 2-point shots plus Y free throws. So the ball went in the basket 22 times. That's what we're looking at. The total quantity was 22 shots. The points, the total points he got was 36. Now for that second equation, X plus Y is 22. For the second equation, you apply the same. It's the number per item times the number of item. Up here I was saying the cost per item times the number of items, but it's just the quantity per item, or the number of points per item times the number of throws. So how many points did he get from all of those 2-point throws? 2 points each times the number of throws. So 2x plus, how many points did he get total from the Y free throws? Y, just 1 times Y is Y. Adding those together, that better give us. Okay. Any questions there? Any questions on our logic, how we set up those equations? We know we need 2 different equations because we have 2 blanks. What? 2 unknowns, 2 variables, so we need 2 equations. Oh, this one's easier. To use elimination. What do y'all think we're going to eliminate, X or Y? Y. Now, I want to minimize the number. Once I add the 2 equations together, I'm going to try to minimize the number of negatives I get. So do you think we're going to multiply the first equation by -1 or the second equation? I think I'd multiply the first one by -1.
Which is exactly the way we've been doing all the others.
Oh, you're right.
Yeah. So we'd have a -x, and then a -y equals -1 times 22 is -22. Recopying. that second equation. If I draw my equal line, are you caught up? Is it going to fall out really nicely? Well, yeah, the y's subtract out. Negative 1x or negative x plus 2x. Is that just going to be
1x.
X equals what? 14. So my answer column.
Make sure you put that on the X row. So 14.
We got 14 2-point shots. Altogether, he scored 22 times. So what am I going to do to the 22 and 14 to get the number of free throws?
Subtract 22 minus 14. He got 8 free throws. So this player made 14 2-point shots and 8 free throws during the game.
Any questions there?
He made.
Okay, so wait. The
14.
2 points up is 14, okay? And now, 8 free throws. We got it done in under an hour.
No, we didn't.
Oh.
Under 2 hours.
Under 2 hours.
Oh.
2 hours,
Okay.
2 hours, yeah. What I was
Okay.
thinking was we still have an hour left. We could go another hour, but we're not going to, of course.